throughout this first month, and I said I'd have more information for you as we got closer to that midterm date. So I had my midterm in my other course yesterday. And again, doing these online midterms is still something I'm kind of learning how to do. So I do kind of have, I guess, a midterm draft, but I'm just going to meet with our senior lab instructor later today and get some feedback on it. So again, I guess the content is going to be similar to other semesters, but the obviously the format being online, I just have to, I've got to tweak things a little bit. So I guess what I can tell you now is that similar to our pre-lecture quizzes, it's going to be in the tests and quizzes kind of section of Connects. And it's, again, the midterm will open up right when our regularly scheduled lecture starts at 9:30 next Tuesday. And at this point, it's looking like it'll be a 45-minute exam. So again, because I know some of you have labs and stuff afterward. So it'll take place during our regularly scheduled lecture. And I'll give you a little bit more information about the types of questions. Again, I've got I guess the general content that I'd like to test, but just I'm gonna again talk a little bit with our senior lab instructor to see if kind of the formats I've got right now work in this setting, or if kind of we can shift them around. As I said, they'll probably, I mean, some of the things I'm thinking about are obviously multiple choice is something that works, but also some of the, like the fill in the blank or short answer types of questions you've seen in the pre-lecture videos. I understand, obviously, with a lot of the discrete math and the asymptotic analysis and proofs, that sometimes doing them in this test and quizzes tool, it's hard to put some of those different symbols in those. So again, that's something that I'm thinking about and trying to come up with a format that works. So Bryce, I don't think people on the midterm will be able to write the exam. People on the waitlist will be able to write the exam. Yeah, at this point, I'm not sure how many of you are still on the waitlist, but I'll email Sue again. I don't know if there's going to be much more movement at this point. I will be on Zoom. So yesterday in my midterm, I was on Zoom. And again, nothing really happened except for people, again, if something came up and had a connection issue, I was there just so people could let me know, and just in case something happened with Connects or something like that. There wasn't any issues yesterday. So again, I didn't really communicate with anyone during the exam, but I will be here during that time, just in case. So yeah, it's possible. So again, I had a bunch of students yesterday that were in the Zoom call, but it was just quiet, just in case something happened. And again, I just stated, and before it started, said, here's just a reminder, here's where you have to click, and it should open up here. And a lot of people, once they actually got into the quiz, they left the call. I think most people are just worried about actually being able to start the quiz. But there were a few people that stayed just in case there's an announcement. I don't expect to make any announcements because again, if there is some sort of clarification issue, I'd want to make sure I could announce it to everyone. So again, what I'll say, and again, I'll have an official Connects announcement once everything's finalized, is again, if there is something ambiguous, just kind of write your assumption down for some of those short answer questions. Well, I've been posting old midterms. Yeah, so I've been in contact with the people that taught this course the last 2 semesters because I've been again trying to align our schedule with theirs and the labs with theirs, and I have some permission for them to share the same practice exams that they shared in previous semesters. So I'll post those this week. Any other questions? So I guess, yeah, another thing I can tell you about the exam is the coverage. So again, obviously it'll start at the beginning where the discrete math unit, and it's going to go through all of the first 5 units. So discrete math, all the pseudocode and counting to runtime analysis, recursion, proofs, and asymptotic analysis. So we kind of had this little side section where I provided some videos just to get people up to speed programming in Java. And then today and this week, we're going to talk about kind of ADTs and sorting. So the Java stuff and the stuff we're doing this week won't be covered. It will be up to and including asymptotic analysis. So because for units 1 through 5, you've had assignments and you've had labs on this material. So I consider that examinable content. Whereas, again, this stuff, as we're just learning this week, it won't be testable. I guess I'll get to the chat in 1 second. So I know many of you, or the assignment deadline for assignment 2 was last night. We are working to try to get that back to you as soon as possible. So hopefully within the next day or two. But I'll post a solution so you can use that to study from after class when I post the lecture videos for tomorrow. People on the waitlist will not be able to take the exam. Yeah, Riley, I'm hoping to. The graders they know that, again, for the grading of the assignment that was due last night, that this one, we'd like to have it back as soon as possible. So they are going to try and get it done as quickly as possible. You'll certainly have my solution, and I'll post that today. But I'm hoping to also have the assignment grades by tomorrow or the next day, so you can kind of see what you did wrong. Assignment 3 is going to be posted next week and due the week after. So yeah, so our last assignment was up to and including asymptotic analysis. We haven't really learned a lot of new content. So assignment 3 will be on the stuff we're doing this week. And as you can see, at the end of this week and into next week, we're going to be working on sorting. So it'll be, I guess, mostly focused on sorting. Any other questions? Okay, so as far as the, yes, I think, yeah, I'll post assignments to both. And again, as I said, you'll hopefully have your grades back as well for assignment 2. And you should already have feedback for assignment 1. So in terms of the, I guess, pre-lecture videos and quizzes, I can see, I mean, obviously I see how many people attempt the quizzes and how well everyone does in the quizzes. And I can also see how many submission attempts people have. And as far as the kind of how well people seem to be able to do on the quizzes, today's quiz seemed to be go a lot better than many of the previous ones. So what I'm going to do really quick is do a quick poll, because I know, or I believe that most of you have probably already done a unit on stacks and queues before, and probably also implemented them and maybe even done some analysis of the runtime of the different stack and queue operations. So I'm just going to put up a poll here to just get an idea of how confident you are in terms of, first of all, implementation of the operations for a stack and a queue, and also just an analysis of the runtime of those different operations. And again, this doesn't have to be in Java. I know some of you, again, only so less than half of you took 115, but again, those of you that did CSC 116, again, this isn't necessarily just a Java implementation, just an implementation in whatever language. Philip, I think at this point, or yeah, by next week, if you're still on the wait list, I mean, again, I'll email Sue again today, but it's probably not looking good because it already has been a month, and I haven't seen a lot of movement with the overall enrollment in the last little while. Okay, so looks like almost half of you are somewhat confident, followed by a lot of you which are extremely confident. That's great. Some of you are neutral and some of you need a refresher. So yeah, I was under the impression that this unit would be somewhat review because, again, as I'm teaching 115 this term, I know that we're covering stacks and queues and implementing them in the assignments and labs. But so I guess this lecture is kind of a transition from a lot of the discrete math and more theory that we've been covering in the first month to kind of shifting towards some of our some more coding, which I talked about how the labs from now on will actually have some coding components as well. And I think the stacks and queues, it's nice to work with something that you've seen before because as we move forward, thinking about different algorithms and data structures, we are, I guess, first and foremost going to be thinking about analyzing them from a runtime perspective. So again, using that asymptotic analysis we've learned, but we're also going to think about memory as well. So again, how much memory is required as our input size grows, and thinking a little bit more of memory. So again, the core thing we're going to be doing with our analysis is going to be runtime analysis, but we're also going to think about memory a little bit. And in some of the other courses, like I know some of you are taking CSC 230 and 360, you'll go a little bit deeper into memory. Whereas now I'm just going to kind of mention, and when we're comparing and contrasting two different algorithms, we'll talk about memory a little bit, but our core focus is going to be on runtime. Yeah, I'll be honest, Andy, I wasn't really sure what the drop date was going to be like this summer with things being as they were. We won't really, Lucas. Yeah, we're not really going to talk about this. So again, from what I got from the previous instructors is a lot of what we're going to be doing in the lectures is going to be more pseudocode, and then the labs and the assignments will give you more of an opportunity to actually think about the more implementation details and some of the, kind of the edge cases associated with that. So I'll talk about it a little bit in the lectures, some of the implementation details, but we're not going to, we don't go extremely deep into implementation details in the lectures. Okay, so yeah, as I said, this will be, I guess, a nice kind of refresher on stacks and queues. And then what I'd like to do, and what I'll do in the pre-lecture videos for tomorrow, is actually talk about a few different implementations just using a queue, and talk about some of the finer details associated with the trade-offs of those different implementations. So yeah, so the worksheet for today is going to be this stacks and queues one. I'll open it up here. And I'd like to move to the stack one quite quickly, and then we'll jump into the queues, which is one that I believe is a little bit more interesting. So starting with this stack example, what we've got is we've got an n element array A that we're going to implement this stack with. So again, this is going to be our array A here. And as we can see, the n is 5 in this case. It can hold 5 elements. And we're going to use an integer variable t, which keeps track of the top element in the stack. So again, I'm starting my t at -1, and as I said in the pre-lecture videos, this is kind of, in some ways we can think of those as referencing where the top element is in the stack. So we're starting at -1 because there's not actually anything in the stack yet. Oh, sorry, yeah, this should be question 1, this tracing this, sorry about that. And so what I want to do is just kind of trace through these operations here and kind of think about what's happening with this array and this variable t as we make these push and pop operations. And we're doing this stack. I've already given you the algorithms here, because what we're going to do is when we move to the queue example, we're actually going to kind of think about what happens when we do our NQs and DQs in terms of the underlying array. And then we're going to kind of, after that, think about the implementation and write those algorithms together. So we know that if we follow the algorithm here and we're saying push an object with value 7 into this stack, again, first we're saying is t plus 1 equal to n, which it's not. That's when we'd have a full stack. Otherwise, we're saying let's make t go up by 1. So it's going to go from 0 up to 1. So now it's kind of pointing to index 0. And then that's where we're going to put that object. Or that integer in this case. And we can see we do the same thing every time. So when we insert the 2, we're going to say, is it full? No, it's not. Okay, my t is going to go up to index 1, and that's going to be where we're going to put that value. Does this make sense so far? Okay, so so now we've done these first 2 operations. Now we're at the pop. And the pop, we say if t is less than 0. So remember, initially t was -1, and that would have meant that the stack is empty, so we wouldn't be able to pop. But since it's 1 here, it's above 0, what we're going to say is the element we're going to, I guess, return is going to be whatever is at the array in that index. We're going to return this 2. And then we're going to make t go down by 1. So again, t is now pointing to here, because we've now kind of essentially removed, we've returned this 2, but we've now removed it from the stack. So the top element is now a 7. We haven't actually done anything with that value in memory in the array, but what we'll do is when we call the pop, we'll get the 2 back to whatever method we call the pop in. And now the top of our stack is essentially pointing to index 0 in the array. Any questions about the pop? Okay. So again, now we're going to push, which is just going to make our t go up to 1. And then we're going to put in the 9 here. Then we know that our t is going to go up to 2, and we're going to put the 1 in. Then we know our 2 is going to go up to 3, and we're going to put the 4 in. We're going to make our t go up to 4, and we're going to put the 8 in. So at this point now our t is 4. Oops. And we can also see here that, and why I made these in this example is because now we see if we try to do another push, we see our t plus 1, so 4 plus 1 is equal to 5. So we wouldn't be able to add any more elements. We wouldn't be able to make any more push operations before first doing a pop. So this is just to show that if I did make another push, we'd see that this if condition would be true. So we'd have to, again, throw an error or do some sort of exception and handle that case where our stack is full. But instead, we're doing a pop, which is again we're going to make sure t is above 0. If not, we're going to say, okay, this is the value I want to return, and I'm going to decrement my t integer, so it's going to go down to 3, representing the fact that it's kind of, our top is now at index 3. Another push is going to return return the 4, and our t is going to go down to 2. And then when we push our last element, again, it's going to, our t is going to go up 1 to 3. And we're going to push the 5 in here. So I guess the final state of our stack at this point is it's got 4 items in it. The top is 5. And again, we have room for at least one more item. Any questions about this? Okay, quick poll. Just for, so there's your understanding on the stacks, and then we'll jump down to the queues. How do we know that? So that, I mean, that was just an example based on, so again, in the lab, when you do a stack, there'll probably be some constant that's your initial size of your underlying array. But that can be, that's going to be something that's different based on different implementations. And you'll, I'm not sure again what you did in your prerequisite course, but often, and this is something that I can think about doing in the labs as well, is you can think about when we're working with a list using an array implementation, how we want to resize that list once our collection fills up. Yeah, so you could have some, you'd have some sort of max size, and when it fills, you would typically, and this is something maybe what we'll do with our list next day. We can focus on this, or at least include this in our example. Is when it fills up, we're going to copy things into another temporary array, and then set that as our kind of main array for the data structure. So T in this example is pointing to the top element in the stack. Which, if you remember our stack ADT, the different operations we have, push and pop, we can check if it's empty, the size, and we can also look at the top value without actually removing it. So the way that we outline the ADT is that pop, again, gets that top item and removes it, whereas that's what pop does. And the difference between pop and top is top just looks at that value. It doesn't actually remove it from the stack. So how does returning the object actually pop? It doesn't, but this T equals T minus 1. So if we popped again and we popped this 5, what would happen is our T would go down to 2, right? Representing that this is now the top of the array. And we know that we'd return this 5 value. So we know that this 5 value is the value that would be returned. So if we've got some pop then our result would be set to that 5. And again, this 5 is still going to be in index 3 in the array. But what's going to happen is if we're saying our T is now 1, when we push something else on top of it, we're just going to overwrite the value at index 3 in the array. So we're not actually clearing anything in terms of memory here. We're not actually removing any of the items here when we pop. We're just keeping track of the fact that our top is pointing to index 2 now if I pop again, when I make that pop, and that is the top element in our stack. Yeah, Lucas. So yeah, we're going to talk about that soon. We're going to go into some of these different data structures, and and there are different implementations of a hash table, and we'll talk about the different of the runtime efficiency of each one of them. So just looking at the polling, it looks like most of you are quite confident with this. So that's great. So we'll move down to the queues unless there are any other questions on this particular example. Okay. So what I'm going to do with the queues is I'm just going to start by doing some NQs and some DQs. I'm not sure why my second one looks a little weird, but so what we're going to do is let's NQ a 2. So we know that 2 is going to be the first item in this queue, or I used like waiting in line metaphor for a queue. So 2's the first thing in line. It's going to be the one that gets removed first. then so this is kind of the first operation. Then after we do the NQ4, we've got a 2 and a 4. Then when we do the NQ of a 6, we've got a 2 and a 4 and a 6. And why I'm writing this out one by one is I want to get us to think about implementation details a little bit here. So now when we DQ, we know that we want to remove this 2 from the front of the list, leaving us with only 4 and 6. But if we remove if we kind of remove the 2 from our array, what do we want to do? Do we want to shuffle all these items over? So then the 4 is at index 0? What do you think? So I'm seeing a yes and a no. I'm seeing a reverse the order. So yeah, so would it work if we shuffled all the items every time we DQ'd? Yes, it would. We could shift it so 4 is now at index 0 followed by 6. And then from then on, we just have 4 and 6 and whatever else we add to the end of the list. But why? What might be one of the problems with shifting or shuffling each item over one index every time we do a DQ? Yeah, so Andy's saying change what 0 means, keep track of where the queue begins and ends. It would be bad for efficiency. Yeah, so I guess one of the key ideas that I want to point out here over on the right is a lot of the same ideas that I'm seeing in the chat. So people are saying change what 0 means, keep track of where it begins and ends. So I'm going to do is I'm going to say, let's keep track of the front and the back of the queue. Sorry, my Zoom call's overlapping. I need to change this. There we go. So let's keep track of the front and back indexes of our queue. So, and what I'll say is that front F index of element at the front, and our B can be the index to insert the next element at the back of the queue. So with that in mind, what we'd have is after this first operation, I could say, okay, the 2's the front, the 2's always the front here. And the index where I'm going to insert the next item would always be the first empty slot. So when I remove the 2, what is going to be the front now? Yeah, the 4. So the 4, so front should now be here. The back's not going to change. But if I remove the 2, I now want to just say my 4 is in front. And I can just, so now I can just change the fact that the F used to be looking at represented by index 0. And now our F could be index 1. So these can both be, we can do this, they can just both be integers. Because they're just keeping track of the index numbers within our array. One where the front is and one, the first, the index where we'll insert our next item. So now if we wanted to think about the pseudocode for our NQ. Right now, we won't even focus too much on checking if it's full or empty. Let's just think about what's the core thing we're doing every time we NQ. Are we doing anything with either our front or back indexes? We'll get there in a second, David. But what are we doing every time? Whoops, algorithm. Every time we add an item. So again, when we added this, so if this was our state at the end of NQing a 2, what did we do to change when we did the NQ4? Yeah, so we're gonna F, we see that F didn't change at all, but B did. B moved 1 forward. So I think what we can think of here is in our array, we're going to put our object in the array at position B, but then we're going to make B go up by 1. So now let's think about this for this next step when we now do an NQ of 8. So what we're saying is we're going to put the 8 into the index of B, which is here, and then make B go forward 1, which is going to make it go from index 3 to index 4. And nothing else is changing. The 4 and the 6 are still going to stay here, and our front is still going to say that it's index 4. What about for our DQ? Keep forgetting to put it in. What do we think is going to happen with when we do a DQ? Yeah, now we're going to do something with front, where I guess the object we want to return. Let me put it up here. So I think there is going to be more stuff I want to do, so I might run out of space down there. So why are we dereferencing? So again, now I've got what operation we have to. We've done our DQ, we've NQ'd 8. So now we're going to DQ here. Again, we know that we want to get rid of this 4. And the front is going to go, that's the object we're going to return. That's going to be our E. And then our F is, we want our F to go up 1 space, so it's now at 6. So if we think about the contents of our array, we've got the 6 and the 8. Again, we've still got these values, these other values that are there. Like we still kind of technically have a 2 and a 4 that are in these spots, but if we're moving our front up to index 6 and our back still at index 4, we're never actually going to look into these spots in the array. And again, I guess the C programmers, which did, or I guess C++, which did this in 1.16, you probably would have had to free memory at this point. But again, if you had an object in this queue, but we're not going to have to do that with Java. We talked a little bit about about how Java's garbage collection works, but I'll make a video again because we're not doing too many programming lectures. So I can do a video on the differences between what you've seen in C++ for allocating and deallocating, I guess, objects and how it's going to work in Java. Yeah, so we're not actually removing any elements. We're just changing where our front and the back indexes are. So we're always working with these save 5 elements in the indexes in the array, but we're never going to actually look at these 2 indexes at this point because our front is here and our back is going to be is over here. So we're only ever going to look at 6 and 8 if we do our DQs. So what I'm saying is we didn't remove 2. I'm just not drawing it in there. I guess I could draw in blue the ones that we removed. So they're actually technically still in the array. We're just they're just not part of our queue any longer. Does that make sense? Okay, great. So now we finished this DQ. So now in an NQ, if you think about what our algorithm's doing, we're saying put this 3 into the index our B is, and then make B go up by 1. So now B is going to be over here at index 5. And what do we think about this? Uh-oh, yeah. So I think Andy's already come up with a suggestion about this. Yeah, David's saying that 5, this B should become 0. Because again, the next empty spot is going to be this 2, which we know isn't part of our queue anymore. Yeah, so I'm seeing some mod 4s. So I guess I'll do one more quick poll because I'm not sure if you did see this in your previous, in your prerequisite course. What I'm going to talk about is the concept of a circular array. And have any of you been introduced to this concept? Yeah, we're seeing some discussion about the mod number, which I think is good discussion to have. We'll talk about this a little bit in a second. Okay, maybe 5 more seconds on the poll. 4, 3, 2, 1. Okay, so looks like, again, about 30% of you are sure you've done a programming course. Another about 30% don't remember. Maybe you did it. Some of you have done it outside of class. Some of you are saying you can guess how it works, which is good. And some of you are wondering what I'm talking about when I'm talking about this circular array. So I guess the idea of a circular array is, so we've got this array with indexes 0, 1, 2, 3, and 4, right? A circular array, we can kind of redraw this as an array where here's index 0, index 1, index 2, index 3, and index 4. Where if we were to kind of visit each index in the array, we could go I is 0, and we could make I go up 1 each time. And we know that I would start at index 0, then go to 1, then go to 2, then go to 3, then go to 4. A circular array does the same thing. It starts at 0 and it goes to 1, then it goes to 2, then it goes to 3, then it goes to 4. But the idea is that if we add 1 to this index, we go back to index 0. So we can keep going around and around and around. And we don't, if we go past index 4, we're not just getting an array index of bounds exception. And we're not, the idea is that when the first index in our array follows the last index. Does that conceptually make sense? Again, not thinking about how we program it yet, but just conceptually, this idea that we could kind of set an array where if we, after we visit the end, we just come back to the beginning again. Okay, cool. So I guess I also have a question, does a circular array still have a front and end? It has different index numbers, and again, it's got an index 0 and an index n-1, but we're going to see that it doesn't necessarily really have to have a start and an end. So I'm going to add this new key idea, and that's going to be this idea of a circular array. And the main kind of point here is that we're going to consider that the index 0 comes after the last index in the array. So what that would do here, coming back to our example, is yes, when B goes up 1 from 4 to 5, instead of going to index 5 here, it is going to go back to and be index 0. Because we're going to say after we go to index 4, and if we go, I guess kind of, if we increment up 1 position, we're going to be back up at the beginning. So how do we do that? Because we can't, obviously we can't just keep making it go up, our B go up by 1, because 4 plus 1 is going to be 5. So what can we do up here? I guess I should say that we've got, let's assume again that this array we're working with has this n, which is 5. We could do it with an if statement. But I'm going to say we don't actually need to even do it with an if statement. I'm doing some other things. So yeah, I'm seeing the modulus. So again, what I'm going to propose is that we do this, where n is the size of the array. So again, let's look at this if we have so let's think about what happens if we add 1 mod n. Again, if we're looping through each of our different indexes, what's going to happen is when we get to 5 mod 5 is just 0. So when we go up 0 up to 1, that's fine. 1 up to 2, 2 up to 3, 3 up to 4. But when we go 4 up to 5, it's if we mod it by n by 5, that's going to go to 0, and then we can kind of repeat this process of going up by 1 again. But now if we look at the larger case, when we've got n equals to 10, a larger array, again, we're going to keep going up by 1, 8, 9. We get to 10 mod 10. Again, that's going to give us 0, and then we can keep kind of going up through the indexes as usual again. So again, our mod, again, using this remainder allows us to effectively wrap around from the last index back to the index 0, and again, treat this as a circular array. So we're not actually creating any new type of array. We're just really doing this kind of trick here that allows us to, when we get to the final index in the array and want to go to the next index, we actually wrap around to index 0 again. And again, the other thing this allows us to do is not have to, when we get to the end here, shuffle all these elements before. Because again, I saw that some people said that we could either make the array bigger or shuffle them. This is going to make it so we don't actually have to do any shuffling. We can just make it so when we add that 3, our B goes to the next empty spot, which is at index 0. In this case, our Q, in this case, our underlying array has a fixed size. Our Q was, the number of elements in our Q was kind of 1, then 2, then 3, then 2. So again, our Q always has a different number of elements in it, but the underlying array, if we choose to implement this with an array, that array will have a fixed size. And again, when it fills up, we might want to, that's something we can talk about next day, think about the best way to resize it, or just say that the array is full. So now, again, we've done this in Q5, or 3. So now if we in Q5, we're going to put the 5 into this index here. And we're saying that the front is still that index 9, but the back now is going to move to here. And now if we kind of think about the order of items in this list, it's actually going to be 6, followed by 8, followed by 3, followed by 5. And the next item we'll insert is going to be right here. We're going to overwrite that 4. I guess first we've got another DQ. So again, this is where we're going to DQ the 6. We're going to have an 8. We're going to have a 3. We're going to have a 5. Our front is going to move to here. And I guess, so we're running fairly short on time. What I want to say is we've also got an issue up here with the front incrementing every time. So if we did a couple more DQs here, our front's going to go over to here, then over to here. So we probably want to do the same thing with the front, right? Because if we DQ the 8 and DQ the 3, the next thing you want to DQ is the 5. So we're also going to want to make it when our front moves up one position that after it DQs the 3 here, the next thing it would DQ would be the 5. Does that make sense? So So the last thing I want to get us to think about, and then as I said, what I'll do is I'll talk about slightly different implementation techniques in the lecture videos that you'll watch for tomorrow. But let's rewind one step to this one right here, where what we've got is we know that the next place we're going to insert is into index 1. So I guess in this implementation, how do we know when, because I guess the last thing we need to think about for our NQ and our DQ is we know that we first want to check if we know that if it's full, we can't NQ. And we know if it's empty, we can't DQ. So we probably want to check if our Qs are full or empty before we do these operations. But how, with this implementation, do we know when our Q is empty or when it's full? Yeah, so if I added one more here, so down here, if instead I added, I did like a NQ 9, 9 works. We know that I'd have 5, and then I'd put a 9 here, 6, 8, 3, and we'd have the F here and the B here. It would be full. But let's also think about if I had a Q here, like this in this first stage here, 2 and 4, when I had the 2 and the 4 in here, let me when I had the 2 and the 4, and we know that my front was here and my back was here, if we do a DQ twice, so again, we first DQ'd out the 2, and then we DQ'd out the 4. We see that our front and back are the same here. So we see that when the queue is full and when it's empty, the indexes of F and B are the same. So that's what I'm going to talk about in the lecture videos. I'm going to talk about, I guess, 3 different implementations of a queue using an array that have very small differences. But what I'm going to focus on is, I guess, the differences in I guess, the slightly different operations we do. One of them has a slightly different way that we're going to detect if the array is full. So we're only going to use 1 less spot. So we'd actually say that this is full when there's actually 1 spot still remaining to be empty, and talk about these slightly different variations of this implementation. And again, talk about it. We're going to see first that they all have the same runtime, but from an asymptotic analysis perspective, but they're going to have slightly different numbers of operations and slightly different ways of detecting if the queue is empty or full. The last thing I'm going to do before we wrap up here is, again, talk about these 2 key points here. The main reason we did them, since we've been talking about asymptotic analysis, is to avoid the shuffling. Again, with this front and this back, we did it so we didn't have to avoid shuffling all the items back to index 0. Similarly, we did this wrap around the circular array, so we didn't have to shuffle all the items back to the front. And we know that these key ideas that they're really, from an asymptotic analysis perspective, these allow us to have a constant time NQ and DQ. Again, no matter how big the input size is, it's always just going to kind of take the same number of operations. Whereas if we had to shuffle all the items left in index every time we did a DQ, again, if we had 1 million items, we'd have to shuffle, make a million different kind of shuffles. So these allow us to make this big O of 1, as opposed to O of n if we had to shuffle. Does that make sense? Because we would have to shuffle all n items, whereas in our case, we're just using these little, these F and B integer variables to keep track of the front and back. We don't have to do any of that shuffling. So it allows us to have constant time operations as opposed to linear O of n. Any last questions about this? Okay, so as I said, I'll talk about, and in the solution I post, I'll actually post 3 different implementations that have, again, these slight variations, and I'll talk about the pros and cons of each, because that's going to be, as I said, going to lead us into our next unit on sorting, where there's a lot of different ways we can sort a list. But we're going to kind of talk about some of the trade-offs associated, first from a running time perspective, but then within things that are classified within the same kind of big O run speed, some of the more finer details associated with memory usage and stuff like that. Any last questions before I stop the recording?